Hi there, welcome to this Elkchemist chemistry video in which I'm going to take you through Hess cycles, specifically those you need to draw when presented with enthalpy of formation data. So, sometimes you might find it's not actually always possible to directly determine the enthalpy change of a chemical reaction. That might be because, for example, the activation energy for that reaction is just too high. Or the reaction has very slow kinetics, i.e. a very slow rate of reaction, so it can't be determined directly in a feasible or practical manner. Or finally, more than one reaction might be taking place at the same time, making it difficult to determine the enthalpy change for the particular reaction you're interested in. That's where Hess cycles come in. A Hess cycle is a thermochemical cycle that allows you to determine that unknown enthalpy change you're looking for using other known enthalpy changes. I'm going to take you guys through the main structure of an enthalpy of formation Hess cycle now. Just before that, I'm going to introduce the key definition for this particular video, which is the enthalpy of formation itself. So, the standard molar enthalpy of formation is defined as the enthalpy change for the formation of 1 mole of a compound from its constituent elements under standard conditions, and with both reactants and products in their standard or reference states. Now I'm going to take you through the main structure of a Hess cycle using enthalpy of formation data. Usually you'll be given an equation, a reaction taking place, i.e. reactants forming products, and often you'll be asked to find out the missing enthalpy change for that reaction using provided enthalpy of formation data. So to do that using a Hess cycle, below that reaction you write the elements in their standard states in the right proportions to form either all of the reactants or all of the products. And then you complete your cycle by drawing arrows up from the elements in their standard state to the reactants and products present. And the key thing to remember here is the arrows go up because formation builds things up. So the direction of arrows is really important when constructing a formation Hess cycle. Make sure the arrows are going up because formation builds things up from their elements in their standard states to the compounds that make up the reactants and the compounds that make up the products. Okay, our first word example is ammonia gas reacting with hydrogen chloride gas to form solid ammonium chloride. Now imagine you're asked to find the missing enthalpy change of reaction for that particular reaction, and you've been provided with some useful data. You've been given the enthalpy of formation of ammonia, the enthalpy of formation of hydrogen chloride, and the enthalpy of formation of ammonium chloride in kilojoules per mole. We're going to apply Hess law to solve this problem. Hess's law states that the enthalpy change of a chemical reaction will be the same, independent of the route taken. Let's consider it with our example here. Our first route is the green arrowed route shown here. Now we don't know the enthalpy change of that route, but if we take an alternative route, the blue arrow directional route we have here, then we know the various enthalpy changes involved in this second route, and Hess's law states that the total enthalpy of route 1 will be equal to the enthalpy of route 2. So if we work out route 2, it will give us route 1 because their enthalpy changes will be identical. A very powerful and very useful idea. Let's now have a go at the actual calculation method. I've tried to make it really easy with a top tip we apply every single time. Draw a circle around the tail of the arrow of the enthalpy change you're looking for, and say you're going to start here. Draw a second circle around the head of whichever enthalpy change arrow you're looking for, and write finish here. And effectively what we're going to do every single time is go around the cycle, starting at the tail of the arrow we're looking for, and going round the cycle until we get to the corresponding tip of the head of that same arrow, and that will be the route we're going to take. Finally, you can see I've transposed the relevant formation values from the little table to my arrow. So there's the arrow representing the enthalpy change of formation of ammonia, hydrogen chloride, and ammonium chloride respectively. Now, really key, notice if we go round this cycle in this direction, we're going to go down these two arrows before we go up this arrow here. So if we go backwards along an enthalpy change arrow, we are doing the opposite of that particular enthalpy change's energetics. So we're doing minus 46, or the opposite of minus 46 kilojoules per mole, and the opposite of minus 92 kilojoules per mole. We reverse the sign. You'll see that in my working, and it's really important to remember that every time we go backwards along an enthalpy change arrow direction-wise, it means we must do the opposite of that particular enthalpy change in terms of energetic process. So let's bring it all together now. we're going against the direction of these two arrows and then with the direction of this arrow as we travel around root 2. That would be minus 46 against direction, minus 92 against direction, plus minus 314 because we're going with the final arrow's direction, and the sum of the enthalpy change of root 2 is equal to minus 176 kilojoules per mole. Now, because of Hess's law, root 2 is equal to root 1 in terms of enthalpy change, so that means we now have also discovered the enthalpy change of the green arrow, which is minus 176 kilojoules per mole. Problem solved. If a student wants to check that that answer is correct, there is a neat little quirk to Hess' law. If root 1 and root 2 are identical in terms of magnitude, then if we go full cycle around our cycle from our starting point back to our starting point, effectively what we're doing is taking away root 1 from root 2. And if they are the same size, that should equal 0. So we can type that into our calculator now and see if our minus 176 kilojoules per mole for our green root is actually correct. Let's work our way around the cycle taking the blue route first. That's going to be minus 46 minus 92 plus minus 314. Then we're going against direction of travel for our green arrow. That's minus 1676, apologies. Taking this full cycle should give us an answer of 0, and it is 0. Perfect. That shows that Hess' law is accurate and in effect, and taking away from root 2, root 1 equals 0, which is exactly what should happen if they are both the same magnitude of enthalpy change. For our second worked example, we're being asked to work out the enthalpy change of reaction for the extraction of iron from iron oxide. That is, iron oxide reacting with carbon monoxide to form liquid iron and carbon dioxide as a byproduct. We've been given the enthalpy change of formation for iron oxide, carbon monoxide, iron, and carbon dioxide, so we definitely can construct a Hess cycle using enthalpy data. The only difference here is that we have some stoichiometry or balancing values, some integers in front of the formulae that have to be factored into our cycle. So we are forming 1 mole of iron oxide, 3 moles of carbon monoxide, 2 moles of iron, and 3 moles of carbon dioxide from the elements in their standard states. Hence, I've done minus 111 times 3 to produce 3 moles of carbon monoxide, plus 14 times 2 to produce 2 moles of liquid iron, and minus 394 times 3 to produce 3 moles of carbon dioxide. But the cycle will work in exactly the same way, which I'll take you guys through now. As before, I've tried to signpost what we're doing and make this as easy as possible for our calculation. So I've put a circle and a starting point around the tail of the enthalpy change arrow we're looking for. I've also put a circle around the head of the enthalpy change value we're looking for, which is our finishing point. We're going to journey around root 2 from the starting point to the finishing point, and that will allow us to calculate the missing enthalpy change. So we're going to be going against the direction of this arrow here, doing the opposite of this enthalpy change, going against the direction of this arrow here, doing the opposite of this enthalpy change, which remember is being multiplied by 3, going with this enthalpy change here, which is remember multiplied by 2, and going with this enthalpy change here, which again is multiplied by 3. And what has appeared now is a summary of that working. Minus 822, because we're doing the opposite energetics of the enthalpy of formation of iron oxide, minus 111 times 3, doing the opposite of the energetics of the enthalpy change of formation of carbon monoxide multiplied by 3, plus 14 times 2, going with the energetics of the enthalpy change of formation of 2 moles of liquid iron, and plus minus 394 times 3, going with the direction of arrow for the enthalpy change of formation of 3 moles of carbon dioxide. The sum of all those various enthalpy changes equals plus 1 kilojoules per mole, which means that root 2's enthalpy change is plus 1 kilojoule per mole. And because of Hess's law, root 2 is equal to root 1, we can assume that this enthalpy change is also plus 1 kilojoule per mole. So we have just found our missing enthalpy change for our root we didn't initially know. Fantastic. Right guys, well done for getting this far in the video. I just want to say, if you find this video useful, please do think about giving it a like. Maybe think about subscribing to the channel. You could even ring the bell to keep notified of our latest content. Trying to put out content on a weekly basis, and your support is hugely appreciated, so thank you so much in advance. Also, you can think about sharing this video or other videos on the channel with friends studying chemistry and spread the learning of chemistry as widely as possible. Thank you so much. Let's look at this last example. Now, example 3 is a little bit different. This time we were given a reaction between hydrogen sulfide and sulfur dioxide to form sulfur and water. But the key difference is you've been given the enthalpy change of this reaction, along with the enthalpy change of formation of hydrogen sulfide, sulfur and water. Therefore, the missing enthalpy change here is the enthalpy change of formation of sulfur dioxide for its elements in their standard states. Don't panic is the key thing. It makes no difference to the way the Hess cycle will work. We're simply dealing with a different enthalpy change of interest. Do exactly the same thing as we've done in the past. Put a circle around our starting point, which is the tail of the enthalpy change arrow we're looking for, and a circle around the head of the arrow we're looking for as our finishing point. We're going to go round the blue route to find the green route. Round the blue route from the tail to the head. Not forgetting this arrow is still here. This is part of the blue route. So we're going to go round our blue route to find our green missing enthalpy change arrow. Let's just talk through the route before I go through the working. So, starting from our starting point here, we're going with this enthalpy change arrow here, which is 3 times 0. Why 0? Well, because in the equation, sulfur is already in its reference or standard state of solid, and therefore there's no enthalpy change required for this formation. We're then doing 2 times the enthalpy change of formation of water, and we're going with this arrow, so there's no need to do the opposite of that process. That's minus 241.8 times 2. Then we're going against the direction of arrow for this enthalpy change for the reaction itself. So we're going to do the opposite of this enthalpy change here. Finally, we're going against this arrow here, doing the opposite of the enthalpy change of formation of hydrogen sulfide, and again, that's times 2 because it is making 2 moles of hydrogen sulfide. So we're going with this arrow, against this arrow, and against this arrow. Let's now see what that working would look like. So our enthalpy change of formation of sulfur dioxide is as follows. Plus 0 times 3 going with the enthalpy change of formation of sulfur. Plus minus 241.8 times 2 going with the enthalpy change of formation of water times 2. Minus 145.6 going against the enthalpy change of reaction for the reaction itself. And minus 20.6 times 2 going against the enthalpy change of formation of hydrogen sulfide times 2. And the sum of our entire blue route from here round to here is minus 296.8 kilojoules per mole. And according to Hess's law, that is equal to our other route, which is our green route here, which means that our enthalpy change of formation of sulfur dioxide must also be minus 296.8 kilojoules per mole. So we've solved this final Hess cycle problem. And well done everybody for sticking with it to the end. I really hope that's helped to simplify and bolster your understanding of Hess cycles involving formation data. This is the first in a series of videos which will cover the Hess cycle, both for formation, combustion and mixed data. So look forward to those in the future. But really great talking to you as always, and I look forward to talking to you in the next video. Take care. Bye now.